In this part, we are going to look at solution stoichiometry, which is something we did in the last chapter when we talked about solution. Solution stoichiometry. And this part is called titration. This is when you have a unknown concentration of a substance, you add to it something known. So for example, let's say I have hydrochloric acid, I don't know its concentration. I would add sodium hydroxide to it with known concentration until the reaction goes to completion as such. Then I can use the information I have from sodium hydroxide, the volume of hydrochloric acid, and I can figure out what the concentration is. This process is known as titration, and it can be applied to anything, just doesn't have to be acid and base, but we're going to focus on acid base here. So you add enough so that the substance that you add to these that would let you know that you have actually reached the end point, or we have equal number of moles acid and base, is called an indicator. Okay, it's called an indicator. Once we reach what's known as the equivalence point, which is the point in the titration when the number of moles I said of OH equals H plus, that indicator changes color. And the indicator that we use usually in Chem 10 lab is phenolphthalein. And this phenolphthalein turns pink, like we see. Phenolphthalein turns pink, like we see in this picture right here, when the equivalence point has been reached. We use that information to back calculate. Let me show you an example. The titration of 10 milliliter of hydrochloric acid. So I have 10 milliliter of hydrochloric acid solution of unknown concentration. I don't know the concentration of my hydrochloric acid. That's what I'm trying to figure out. If I titrate those 10 mils with 0.1 molar sodium hydroxide solution, I'm going to need 12.54 milliliter. That's what this problem is saying. In order for me to reach the equivalence point, I need 12.54 milliliter 0.1 molar sodium hydroxide solution. What's the concentration of hydrochloric acid? So what we want to do, we want to use the volume of sodium hydroxide, multiply that by the molarity of sodium hydroxide. This will allow me to convert from volume to moles of sodium hydroxide. Then I need to write a balanced chemical equation for the neutralization reaction between hydrochloric acid and sodium hydroxide, to use it in order to derive a ratio, stoichiometric factor, in order to go from moles of sodium hydroxide to moles of hydrochloric acid. Once I get the moles of hydrochloric acid, then I can divide it by the volume I have of hydrochloric acid, and that would allow me to calculate the molarity. Keep in mind, the volumes have to be in liter. So I'm going to start with 12.54 milliliter of sodium hydroxide, convert it to liter, then use the molarity of sodium hydroxide as a conversion factor. It's 0.1 molar. That means I have 0.1 mole sodium hydroxide in 1 liter of sodium hydroxide. This would allow me to get moles of sodium hydroxide. I'm going to use the 1-to-1 ratio from the equation right here. 1 mole of hydrochloric acid over 1 mole of sodium hydroxide would allow me to figure out how many moles I have of hydrochloric acid. Then I take that number, moles of hydrochloric acid, divided by the volume that was given to us, and I can calculate molarity of hydrochloric acid. Now your turn. Try the following. I've given you the balanced equation here. Pause the video, try it, and come back and check your answer. Alright, so we're given the volume of barium hydroxide, the molarity of hydrochloric acid, 0.107 molar, and the volume of hydrochloric acid. Alright, I want to figure out the molarity of barium hydroxide. The difference between this problem and the previous problem that we're looking for the concentration of barium hydroxide, which is the base. Also, it has 2 hydroxide. That means I need twice as much hydrochloric acid. That's where stoichiometry comes in. So again, I'm going to go from volume of hydrochloric acid to mole of hydrochloric acid by using its molarity. I'm going to use volume and molarity to figure out the moles. Then from the equation right here, the balanced equation, I'm going to use the mole to mole ratio to figure out the moles of barium hydroxide. Once I have moles of barium hydroxide, I can divide it by the volume of barium hydroxide to get molarity. All right, let's solve it. So we start with the volume of hydrochloric acid. I need it in liters, so I'm going to convert it to liter. Then I'm going to use the molarity of hydrochloric acid to convert to moles of hydrochloric acid, then use mole to mole ratio. Notice 1 mole barium hydroxide requires 2 moles of hydrochloric acid. 2 moles. All right, this would allow me to figure out the number of moles of barium hydroxide. Once I have the moles of barium hydroxide, then I'm going to divide it by the volume of barium hydroxide, 3.76 times 10 to the negative 2 liter, and I get 0.0623 molar barium hydroxide. The next part of this chapter, we're going to explore the strength of an acid and base just briefly. So anytime we're talking about an acid and a base, so let's take a look at, for example, hydrochloric acid versus hydrofluoric acid. They look the same. Hydrochloric acid on the periodic table, Cl is just below F. So they should be similar, but they are not. Hydrochloric acid is a strong acid, whereas hydrofluoric acid is a weak one. And the difference would be that for a strong acid, it will completely ionize in water. And we usually use a single arrow to indicate that complete ionization. That means we're going to get all of it will exist in ion form. We get complete ionization. We're going to assume 100% ionization as such. Okay? Now, because it completely ionizes, we can consider this to be a strong electrolyte, right? It will conduct electricity very nicely, and strong acids are considered strong electrolyte. And as I gave you in chapter 7, there are 7 strong acids. In addition to these 6, I want you to add chloric acid, HClO3. Notice that all of those strong acids are monoprotic acid. That means they have only one acidic proton, HCl, HBr, HI, HNO3, and HClO4, one proton. Whereas sulfuric acid is a diprotic acid. Keep in mind, only the first proton is strong. The second is not. All other acids that are not part of these 7 strong acids right here, again, I told you to add chloric acid, HClO3 here, are weak acids. So weak acids only partially ionize in water. So a very small percentage of weak acids will actually ionize. Okay, not a lot, only partially. And we use this double arrow to indicate that partial ionization. Most of the compound will stay in intact form, as you see right here. As a result, we have very few ions in solution. Therefore, weak acids are considered weak electrolyte. They give us a dim light. Okay, they are weak electrolyte. These are some common weak acids, such as hydrofluoric acid, acetic acid, formic acid, sulfurous acid, carbonic, and phosphoric acid. Those are weak acids. How do we determine the concentration of H3O plus in solution? So if I have a strong acid, the concentration of H3O plus will be equivalent to the concentration of the acid. If I have a weak acid like this one, then I can't. It's going to be much less. Okay? HCl is a strong acid. It completely ionizes. Therefore, the concentration of H3O plus is 1.5 molar. For acetic acid, because it's a weak acid, it partially ionizes. Now we're not going to discuss how we can. There is a way to actually calculate exactly what the concentration of H3O plus would be for acetic acid, but it's beyond the scope of this class. If you go on and take Chem 12, then you can learn it there. So for now, we're just going to say it's less than the concentration of the acid. Nitric acid is a strong acid. That means it completely ionizes. Therefore, the concentration of hydronium is the same. Strong bases, on the other hand, those are the bases that completely dissociate in solution. And those are group 1 and group 2 metal hydroxide, such as lithium hydroxide, sodium hydroxide, potassium hydroxide, strontium, calcium, and barium hydroxides. All right? This one will completely dissociate in solution. So they are strong bases. They do contain, so anytime you have a metal hydroxide and that metal is group 1 or 2, it's going to be a strong base. Weak bases, on the other hand, will have that double arrow and only partially ionize in water to give us hydroxide. Some examples of weak bases are right here in this table, and those probably the ones we're going to see. I don't want you to worry too much about pyridine, methylamine, and ethylamine, but what I want you to know that there are derivatives of ammonia. Notice they all contain nitrogen and they are derivatives of ammonia. Just the only thing you need to worry about. So ammonia and its derivatives, as well as carbonate or bicarbonate ion. Those are weak bases. So let's see if we can determine the hydroxide ion concentration in solution. I'm given these, so let's examine them one at a time. KOH is a strong base. It will completely dissociate, same concentration. Whereas methylamine is actually a weak base, then the concentration is going to be less. Strontium hydroxide is a strong base, and because strontium is going to give me twice as much hydroxide, I'm going to multiply it by 2. So it's 0.05 molar, the concentration. All right, 0.05 molar. Now water, as we learned, is an amphoteric substance that can act either as an acid or a base. Let me actually come back to the water thing.